So we're going to go over some of the problems, some of the math for what we're learning right now as we end the unit on more about waves, but we're looking at light waves. So we'll talk about the speed of light, where we're going to define c as 186,282 miles per second. I do think it's important that you try these on your own, and I'll show you how I went about solving them. So these should help you with some of the practice problems, practice quizzes, and the practice lab exam to work from. So what is the time it takes for a photon to travel from the sun to the Earth? Well, if I know it's 93 million miles away, I'm really using velocity distance time. I'm solving for t is going to be the distance divided by the velocity. In this case, it's c. I can take 93 million divided by 186,282 miles per second, and I get 499 seconds. So essentially 8 minutes and 19 seconds. When I solve from the moon to the Earth, same equation applies. T is equal to distance divided by velocity. In this case, the velocity is the speed of light. 240,000 miles from the Earth to the moon divided by the speed of light, and I get 1.3 seconds. So the light we see on the moon has taken 1.3 seconds to reflect from it and reach our eyes. But then we solve for the sun to Mars, which is 1.5 AUs. So t is equal to distance divided by the speed of light, but I have 1.5 AUs times 93 million miles divided by 186,282, and I get 749 seconds. And now if I solve, how long does it take a photon leaving the sun to get to the average distance from Neptune, which is 30 AUs? So t is equal to distance divided by the speed of light. 30 AUs times 93 million divided by 186,282 miles per second. I get 14,977 seconds, which is about 250 minutes, which is 4.1 hours. Now remind you, I'm just giving you examples of problems to help you solve them. Now we're going to solve a light year. That's the distance traveled by a photon in 1 year. Now we're assuming it's traveling through the vacuum of space. So what is the distance a photon travels in 1 year, right? This is a light year. So I know the speed of light is 186,282 miles per second times 3,600 seconds in an hour. That's essentially like taking times 60 seconds in a minute times 60 seconds in an hour times 24 hours in a day times 365 days in a year. And I get this really big number, 5.87 times 10 to the 12th miles. So this value here is my value in miles. What distance has it traveled? Oh, excuse me. If I multiply this times 3.1 years, I get 1.8 times 10 to the 13th miles. Now I can take that value and divide it by, I know that 1 AU is 93 million miles. I divide it by 93 million, and I get, well, let's see, what is it? 195,820 AUs, or 1.96 times 10 to the 5th AUs. So once again, you're just getting practice, a little bit of familiarity on here, and you'll be asked to solve this in the near future. So here we look at light intensity in the inverse square law. But I want you to see that the further you get from a light source, the less intense or less bright that light is. Therefore, the closer I get, the brighter or more intense that light is. So a light source generates 4,000 watts per meter squared at a distance of 100 meters. What is the light intensity at 50 meters? Well, 50 meters is 1/2 the distance of 100 meters. So it's going to be, so half the distance is 4 times more intense. So 4 times the original intensity of 4,000 watts per meter squared is 16,000 watts per meter squared. Right? This larger value tells me that it's more intense. It's brighter. The 200 meters is twice as far, so it's 2 times further. It's going to have 1/4 the intensity, so 1/4 of 8,000 watts per meter squared is 2,000 watts per meter squared. 25 meters relative to 100 meters is 1/4 the distance, so it's going to be 16 times brighter. And I can take 16 times 4,000, and I get 64,000 watts per meter squared. And lastly, 400 meters is 4 times further. It's 1/16 the intensity. It's going to be 1/16 of 8,000 watts per meter squared, so it's going to be 500 watts per meter squared at 400 meter distance. Here I can look at the refractive index and changing the speed of light through different media. In order to solve this, you have c, the speed of light in a vacuum of space, is 3 times 10 to the 8th meters per second, or 300 million meters per second. That's the same as 300,000 kilometers per second, and that's the same as 186,282 miles per second. But we'll go with meters per second. We get a better way in which we can calculate numbers. We can see the difference between them. So based on the known n values, what is the speed of light as it travels through the vacuum of space? Well, that was given. That's 3 times 10 to the 8th meters per second. So now I'm going to start solving, and I'm going to use this equation that I'm going to need to know here. So I can use this equation. Index of refraction equals the speed of light in a vacuum, which is c, divided by the speed of light in a material. So we're isolating and solving for speed of light in a material. So the speed of light, c, in a material is going to equal the speed of light in the vacuum divided by n. So I essentially cross multiply these two. So I'm solving for this, and I get speed of light divided by the index of refraction. So for ice, well, ice has an index of refraction of 1.31. So I can take this, so I'm solving for the speed of light in a material, and that material is ice. So 3 times 10 to the 8th meters per second divided by 1.31, right, the n value of ice, and I get 2.3 times 10 to the 8th meters per second. And if you look at your calculator, it's not in scientific notation, it's 229,000, let's see, 229 million, 7,634 meters per second. So now I'm going to have you solve for what's the speed of light traveling through a diamond, which is an n value of 2.42. So 3 times 10 to the 8th meters per second divided by 2.42, that's the n value in diamond. It's 1.2 times 10 to the 8th meters per second, which is 123,966,942 meters per second. And lastly, slide 5. Refraction. As a photon, as a wave enters a new boundary, it refracts upon entering a material with a different n value, and its speed changes as a result. So refraction is really just illustrating a change in speed. It refracts as its speed changes. So I say draw a ray diagram for the following. Sunlight travels from space into the Earth's atmosphere. So I know the vacuum of space is an n value of 1, and the vacuum, or the n value of air is 1.0001. So I give you that in this table here. So the incident ray, the light's coming in at some angle. I have to draw my normal line at the point of contact with the new boundary. It's going from the vacuum of space into air. I have to draw my normal line perpendicular to the boundary. This is my line. It's going to refract. It's going to bend toward the normal line. If I'm going from a low n value to a high n value, the refraction is going to bend towards the normal line. And here I see, or I'm having you draw a ray diagram for sunlight that travels from the Earth's atmosphere into water and then into ice. So I've got 3 boundaries here. I have the n value of air of 1.0001, water 1.33, and ice 1.31. So I have my boundary lines drawn here. And I have this angle, this incident angle coming in at this angle. It's going to go from low to high. Low to high, it's going to bend or refract towards the normal line. So it's going to bend towards this normal line here, but it's going to keep traveling in a straight line. In this case, it's going to go from high to low. When it bends from high to low, it's going to refract, it's going to bend away from the normal line. So notice this incoming angle relative to the normal, this theta, is going to be smaller than its refractive angle, which is going to be greater here. So it's going to bend at a greater angle because it's going to bend away from the normal line. Hope this helps.